The Renaissance was the period of the great flowering of literature, philosophy, art and science in Europe in the 15th and 16th centuries. For mathematicians, it's especially associated with the rediscovery of Greek learning, following the translation of Euclid and other Greek mathematical works into Latin, both from the Greek and from Arabic translations. But all this has tended to overshadow another and parallel tradition of vernacular works, that is, works written in the languages of the people, concerned not with scholastic learning, but with the practical problems of commerce and everyday life. These works were also responsible for the popularizing of the Hindu-Arabic numerals in Europe, and for the demise of the counting board and the cumbersome Roman numerals. It's this tradition that we're now going to look at, examining some of the calculation methods used and tracing the numerals back via the Arabs to India. Towards the close of the 15th century, two remarkable vernacular works appeared. One, published in Venice, had considerable influence. The other, written in Lyon, remained virtually unknown for almost 400 years. The author of the Italian work was a friar, Luca Pacioli. Born about 1445, he was a private tutor in Venice, where he also joined the Franciscan order, later moving from city to city as a public teacher of mathematics. Here in Cambridge University Library, we have his most influential work, the Summa de Arithmetica, Geometria, Proportioni et Proportionalita. It's a summary of the basic mathematical knowledge of the time, printed in 1494, just 16 years after the first printed arithmetic published in Treviso, near Venice. To our modern eyes, it's a difficult book, with its 600 pages of close print and its unfamiliar abbreviations. The geometrical section is just elementary geometry with practical applications. But the section on commercial arithmetic is famous for the first published account of double-entry bookkeeping. But here we're concerned with arithmetic and algebra. So let's look at where Pacioli is discussing problem solving using algebraic methods. In solving a commercial problem, Pacioli arrives at this expression. Let's interpret it. First, co is short for cosa, literally thing, the unknown quantity, Rx. So here he has a half x. Ce is short for censo, a square, that is, the square of the unknown. P is short for più, plus. There's no symbol for equals, here it's written in words. In solving this equation, he gets this. Here, capital R means radice, the root of whatever immediately follows. The men is meno, minus, often written just as the letter M. So this means root 625 minus 1, which is just 24. In another problem, when he wants to express the square root of a series of terms, he uses this symbol. He calls it the radice universale. It just means this. But now, let's look at this. Here, he's using a small letter r to mean the square root of the number immediately following. But what we can't tell, except from the context, is where the end of the first universal root is. In fact, the expression means this, but it could just as well have been this. He also uses r to denote powers, but his first power means rx to the power of naught, his second power rx, and so on. We have to take great care reading Pacioli's text. The other important vernacular work was written by a Frenchman, Nicolas Chouquet. We learn from his manuscript that he was a Parisian, a bachelor in medicine, and that he lived in Lyon. We also know that he was a professional letter writer and an algorist, a teacher of calculation. Chouquet's manuscript consists of a three-part work on arithmetic and algebra called the Triparti, plus an appendix of problems, a geometry, and a commercial arithmetic. It's remarkable for its innovations, especially in notation and in the algebraic methods used. Here, for instance, Schucke is simplifying an algebraic equation. First, this means square root, and it's easily extended to the cube and other roots just by changing the numeral. Also, he uses underlining to show precisely what a root acts on. Here's p for plus again, but don't be misled by these indices. They don't refer to the numbers, they mean powers of the unknown. So this is actually our 4x squared, and this is 4x, and this 2x. But now look at this page of the manuscript. This is quite new. The index 0 is used with the number 72. It's as if we wrote 72x to the power of 0. It's divided by 8/3, r 8x cubed. Schucke's result is 9/3m, that is r 9x to the power of -3. And it's clear that he understood a negative index as a reciprocal. This is quite remarkable for his day. Schucke's symbolism was way ahead of its time, but it had little influence on the subsequent development of notation. This is because of its subsequent history and because it wasn't printed. It fell into the hands of one of his pupils, Etienne de la Roche, who plagiarized large parts of it under his own name as arithmetic newly arranged. Unfortunately, he left out the more original parts. Schucke's manuscript had a checkered career until its rediscovery in the 19th century. From these 2 pages, we can tell that it passed through a number of private libraries, eventually ending up in the Bibliothèque Nationale in Paris. But the library catalogues gave no hint of Schucke's algebra. So when the Tripartite was published in 1880, it created a sensation, for Schucke had been entirely forgotten. Pacioli's Summa is in a long tradition of vernacular Italian works in which problems of commerce played an important role. In fact, Schucke's work is also linked to the same tradition. We know Lyon was an important center of the spice trade between the Middle East and Western Europe, and that it had a large Italian colony. This tradition of Italian manuscripts, stretching back to the 13th century, has been largely ignored until recently. They all owe much of their inspiration to one particular work, the Liber Abaci, written in 1202 by Leonardo of Pisa, often known as Fibonacci. Here it is, in a printed form published in 1857. It's mostly remembered today for a sequence of numbers now called the Fibonacci sequence. It arises out of a problem concerning the breeding of rabbits. Each number is the sum of the preceding 2 numbers. It's remarkable because of the number of ways in which it turns up in nature, but its mathematical properties weren't appreciated by Leonardo or his contemporaries. They became known only in the 19th century. What's of more interest to us is that the Liber Abaci revolutionized the low-level mathematics of the West by promoting the Hindu-Arabic numerals and the methods of calculation that went with them. Leonardo was born in Pisa around 1170, a member of the Bonacci family, hence Fibonacci. He tells us about his life in the preface to the Liber Abaci. He was brought up in North Africa, where his father was a local official in the Italian trading colony at Bougie. From a Muslim teacher, he learned calculation using the Hindu-Arabic numerals. He traveled extensively on business trips before returning to Pisa to write the Liber Abaci and other works. He appreciated the benefits for merchants in calculating with the Hindu-Arabic numerals, which were far easier to use than Roman numerals. One great advantage over the counting board, the abacus, was that there was a record of stages of calculations which could be checked. The manuscript begins by describing the basic arithmetical operations using the new numbers. Here's the result of the multiplication of 37 by 49. Leonardo then checks this using a method known as casting out nines. We first add the digits of each of the numbers to be multiplied. 9 and 4 is 13. We then cast out the 9. That is, we divide by 9, leaving remainder 4. 7 and 3 is 10. Divide by 9, and the remainder is 1. Now for the product. 8 and 1 and 1 and 3 is 13. Divide by 9, and the remainder is 4. We now just check that the product of these two remainders is the same as the remainder from the overall product, which it is. Here, Leonardo writes that his calculation is proved by the number 4. One problem-solving method used by medieval mathematicians and promoted by Leonardo was the rule of double false position. Let's look at a typical example. A merchant travels between 3 cities in Italy. He goes from Lucca to Florence and then on to Pisa. In each city, he doubles the amount of money he entered with and then spends 10 denarii. He ends up with no money. So how much did he start with? We begin with a guess. Suppose he starts off with 12 denarii. At Lucca, he doubles this to 24 and then spends 10, leaving 14. At Florence, he doubles this to 28, spends 10, leaving 18. At Pisa, he doubles this to 36, spends 10, leaving 26. So at the end of his travels, he's left with 26 denarii, which is 26 too much. So we make a second guess. Suppose instead he starts off with 11 denarii. It turns out he now finishes with 18. There was a standard diagram for getting the final answer. We put the guesses on the right and the amount by which the answers were wrong on the left. We now just follow the diagram like this. The advantage of these methods was that they could be carried out by rote without having to form and manipulate algebraic equations, for which there wasn't any adequate notation. Now, the Liber Abaci owed its inspiration to Latin translations of Arabic works, and especially of an arithmetic and an algebra, written by the great 9th century Islamic astronomer and mathematician, al-Khwarizmi. His family came from Khwarezm, hence al-Khwarizmi. We know that he was a member of the House of Wisdom, a scientific community in Baghdad, established at a time when both Greek and Indian works were being translated and studied. His arithmetic is lost in its original form and exists only in Latin versions, but the algebra exists in its original Arabic as well as in Latin. Its fuller title is Al-Jabr wal Muqabala. The modern word algebra is derived from the first word in the title. Al-Jabr literally means completion and referred to the process of eliminating negative quantities by addition to both sides of an equation. Here, by Al-Jabr, we eliminate the minus 10x on the right by adding 10x to both sides. The word al-Muqabala meant balancing and referred to the process of eliminating positive terms by subtraction. Here, by al-Muqabala, we take 3x squared from both sides to give this. Of course, al-Khwarizmi didn't have our algebraic shorthand at his disposal. His equation would be written out in this form. But by the methods of al-Jabr and al-Muqabala, all quadratic problems could be reduced to one of these 6 types, with the coefficients always positive, as mathematicians didn't generally accept the existence of negative quantities. A negative length, for example, was inconceivable to them. Here's how al-Khwarizmi justifies his solution to this equation. He first draws the square of the unknown. We call this side x. Now he adds the equivalent of 10x, 4 rectangles around the edges, each of area 2.5x. So this area is equal to the left-hand side of the equation, which is equal to 39. Now he completes the square by adding 4 squares, each of area 6.25. So we've added an area of 4 times 6.25 to the previous given area of 39, making the total area 64. So this side is 8, which is 2.5 plus x plus 2.5, which is x plus 5. So x is 3. Al-Khwarizmi was able to justify methods for solving the other types of quadratic equation using similar drawings. These methods were used in Islamic countries for problems of determining inheritance or land distributions. So we see a continuous tradition of algebraic and numerical problem solving stretching back from Pacioli and Schuke through Leonardo to Al-Khwarizmi. Although Al-Khwarizmi wrote his quadratic equations entirely in words, he did know about the Hindu-Arabic numerals. Indeed, we know from the Latin versions that his arithmetic introduced them. But what we don't know exactly is how they were presented in his original Arabic, because translators often made alterations. But we can trace the origin and development of these numerals and their transmission to the West. They'd come from India to Baghdad with manuscripts brought by trading caravans. The first of these, probably a work on astronomy by Brahmagupta, arrived around 770 AD. The Islamic Empire extended as far as the Indus Valley, but the earliest numeral system there was just a simple tally system. Here are the Brahmi numerals from the 1st century BC. There are distinct numerals for 1 to 9, though 2 and 3 are of the tally type. Then 10 to 90 are distinct, and also 100 and 1,000. Multiples of 100 and 1,000 are just combinations with unit symbols. We can begin to see some of our own numerals taking shape, especially 6 and 7. There's no 0, because place value wasn't yet involved. By the late 6th century AD, these numerals had developed into the Nagari numerals. It's not difficult to see how these came from the older Brahmi ones. Let's see that again. Notice 2 and 3 are very like our own forms. The Nagari numerals were used with the place value principle, so separate symbols were only required for 1 to 9. The position of the digit determined its value. So that here, for instance, we have the symbols 3, 4, and 6 to represent 346. Place value also made it essential to have a 0. Here's a 7th century example from as far away as Cambodia, the number 605. The 0 is represented by a dot. The earliest reference to the numerals west of India was by a 7th century Syrian scholar, the Nestorian bishop Severus Sebocht. He refers to what he calls the Indian subtle discoveries in astronomy, including calculation with 9 symbols. After the arrival of the Brahmagupta manuscript into Baghdad, the existing Arabic system was replaced by the Hindu numerals, which in the Islamic world gradually evolved into 2 separate forms. These, the East Arabic numerals, are those in use in the Arab world today. The West Arabic forms first arrived in Europe through Spain and Sicily. The oldest European text introducing the numerals is Spanish, the Codex Vigilanus. It dates from the second half of the 10th century. Here's where the numerals are introduced, but without the 0. But such early attempts to promote the numerals in Europe failed. A second attempt, this time by Gerbert, later to be Pope Sylvester II, introduced the numbers on the counters used on the counting board. This failed because it proved less convenient than the normal practice of using unmarked counters. The numerals, as on the counters, appear frequently in 11th and 12th century works. But because the counters can rotate, a numeral like this could appear in any of these forms. With the appearance of the Liber Abaci in 1202, the written arithmetic began to compete seriously in Europe with the counting board and the Roman numerals. For some 200 years, a battle raged between the innovating algorists and the conservative abacists. Here in this 16th century woodcut, the contest is delightfully portrayed as being between Pythagoras, using the abacus, and Boethius as the algorist, with Dame Arithmetica looking on. The sour look on Pythagoras' face shows that he's the loser. The eventual victory of the algorists was delayed not only by conservative opposition, but also by suspicion on the part of the banking community, which issued dire warnings about the ease with which the numerals could be falsified. An edict was passed in Italy requiring sums of money to be written out in words, as well as in the numerals. And we still write out our checks like that today. But as knowledge of the written calculation method spread, so did the realization of the advantages over the counting board and Roman numerals. The Hindu-Arabic forms continued to be written in many different ways, as we can see from this table, compiled from medieval manuscripts. It was only when printing became commonplace that the forms of the numerals standardized into those we know today. There's one final stage we can trace in the story of the Hindu-Arabic numerals, that of decimal fractions. The early users of the numerals didn't extend them to fractions, though Islamic scholars did provide the first impetus when they expressed the fractional part of highly accurate computations of pi with denominators which were powers of 10. Sometimes the denominators were omitted and a vertical bar was used to separate the fractional part from the whole number. This practice of omitting denominators was continued in Europe, but no general extension to fractions was possible until a popular account was available. This was provided by Simon Stevin, a Flemish engineer, who was also responsible for introducing Pacioli's double-entry bookkeeping into the Low Countries. In 1585, he produced a pamphlet entitled De Tiende, or La Dîme in the French version, the 10th part. Here he explained for the first time calculation with decimal fractions. We see from these pages how he indicated the units place, and then tenths, hundredths, and so on. All that's missing is our decimal point, which makes the circled numbers superfluous. This came in the form of a colon, a line, a comma, or a dot, within a few years of Stevin's work, and thus completed the decimal numeral system which we all use today.